Today we're going to talk about orthogonality and the inner product. And we're going to be switching gears here a bit. So previously we've been talking a lot about deriving partial differential equations. And right now we've learned a few properties about partial differential equations. But in order to go further, we need to acquire more tools. So the goal here is to acquire more tools. Acquire more tools to develop methods to ultimately solve PDEs, such as the heat equation and other PDEs as well. Okay, so we need to acquire more tools, and the tools we need to acquire are they're geometric tools. They're tools that help us understand some notion of angles. So in order to do this, we need to kind of go back a ways in time and go back in our education and talk about vectors again, and particularly vector spaces. And we're going to restrict our attention first to vector spaces like Rn. But we'll also do function spaces. All right, we're going to develop some tools that go along really well for vector spaces that help us understand something about vector spaces. So let's talk about orthogonality. So recall that we have two vectors. Let's just pick an example, v1. It's just going to be equal to the vector, we'll call it 1, 2, and v2, which we're going to call, which we'll say is negative 2, 1. All right, so if I were to plot these two vectors like that, we'd go 1 up and then 2 over, like that. And then we can go negative that direction 2 and then 1 up and draw that. And we can see that these two vectors are at 90 degrees. Okay, so there's something nice about these two vectors that and we call this perpendicular. We know that lots of things in our world are perpendicular. We want to generalize this concept. So the goal here is to generalize this concept of perpendicularity. We're going to do it. We're going to generalize it to high dimensions. And when we go to high dimensions, we don't call it perpendicular anymore. We call it orthogonality. So that's the word of the day. Okay, so let's discuss this. So the one tool we have so far is called the dot product. And we've been using this tool quite a bit so far in this class. And if I have two vectors, v1 and v2 here, we know that that's going to be equal to 1 times negative 2. So we multiply this number by that number, and we those two numbers, then we multiply these numbers and those numbers, and we add all of those products together. So that becomes 2 times 1. And that is negative 2 plus 2, and that's equal to 0. So we know that if the dot product between two vectors, any two vectors, is 0 in R2 or R3, we know that there's a 90-degree angle in between. But it turns out we can define a dot product, of course, for vectors that are much big, that have more than 3 dimensions. So we can say v is of the form a1 all the way to an, So it's an element of Rn, where n can be any number now. And we say that the same thing is true for some other vector u, b1 all the way to bn. Those are two vectors. And then we say that the dot product between the two of those then is going to be the sum of the product of each term, of each entry of each vector, I equals 1 to n. All right. And now what we'll say is then, we'll say u and v are orthogonal if, and only if the dot product of both of them, the dot product is 0. With one exception, we assume, I'll put a little asterisk there, assume u and v are not 0. They're not the 0 vector. We have to be non-zero, otherwise it's trivially true. Okay, so we want to generalize this notion, and we have so far. Now the dot product can work in high dimensions as well. All right, so let's kind of explore, dig a little deeper to explore why we can get a sense for perpendicularity, and more generally a sense for angle. The idea that, so we have what we call a dot product, and more generally we're going to call this dot product is actually what we call an inner product. So we can put u dot v, or we can use a different notation. We're going to use angle brackets. So in previous lectures and other notation that's used in our textbooks, we use something like this for vectors. So the whole thing then would be a vector. But not anymore. Now we see an angle bracket with a comma. In the context of inner products, this is what we call an inner product, and it's actually going to be a function that takes in two vectors, in Rn for now, two vectors in Rn, we'll put a little cross there, and it outputs a number, a real number, R1. Okay? And of course that's exactly what a dot product is, but we're going to generalize this notion of inner product and get some ideas here. So first of all, some rules of inner products. Okay, so the first rule will be one of symmetry. So we need to have u, the vector u, and the vector v. The inner product has to be symmetric. It doesn't matter which order you put the inputs to the two things. They're both going to be equal to the same thing. The other is linearity. And that is that u and v plus w, if I have the sum of two vectors, it passes through, sums pass right through the inner product, and it becomes the sum of two individual inner products of the two summands, right there and there. Okay, and there's the other property of linearity. I'll actually put them in a bracket here, that if I have a scalar, so that's a scalar, a real value, or complex, it could be complex, that they can move through the inner product as well. And you can verify these properties for the dot product for sure. And we'll develop some other examples of inner products that aren't the dot product. They're defined differently, and they work on different vector spaces, including function space. We'll do that a little later. And then the final property, which is that what I'll call positivity, and that's that the dot product of any vector with itself is going to be greater than or equal to 0, and equal to 0 only if u is equivalently the 0 vector. Okay. So remember what's really important. The other thing that's important here is we have this notion of length of a vector. And I usually put it in double absolute value symbols. And this represents vector length. So for vectors in Rn, we know that this is the square root of a1 squared plus a2 squared plus a3 squared dot 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 all the way to an squared. All right, so we should be able to, we're actually going to rewrite this as follows. The sum of squares, of course, is exactly what a dot product is. So that's actually just u comma u. And we just take the square root. So we can always define our vector length function in terms of the inner product in this way. Okay, and this is true for this particular inner product that we have here. We might have to do a little something else, but there's always a relationship between the inner product and its length through some sort of transformation. In this case, it's a square root. In other cases, it may not be a square root, but for the cases we're going to deal with today, it'll always be the square root of the inner product. That's how you get the vector length. Okay, so the second property that is very important now is something called the Cauchy-Schwarz identity. So SCHW, the Cauchy-Schwarz inequality. Apologies for the poor handwriting there. It's a very neat property. It says that the length of hold on, the dot product of u and v is always the absolute value of it. Remember, this spits out a real number, is going to be less than or equal to the magnitude of u times the magnitude of v. All right. So what's some other ways of writing this? So you can look in the book for a proof of this. It's not too hard to prove, but let's just explore some of the consequences of this relationship here. It says that once we know the magnitudes of u and v, we know whatever the dot product is always going to be up to whatever the sign it is. It's always going to be less than the product or equal to the product of the lengths. So it gives us a nice bound for what the inner product is. We'll tell you some consequences of this. So we'll just rewrite this. We'll take off the inequalities, and then we know that, or sorry, we'll take off the absolute value here and put the dot product like this. And we'll say that this is, now of course lengths are always positive. And then we have the same thing on this side, the negative version of it. Okay. So we know that now we've been able to bracket our dot product between the positive product of the vector lengths and the negative product of the vector lengths. All right, so one thing we can do is, of course, divide the whole thing by the product of the vector lengths. And then we get minus 1 u dot v all over u and v magnitudes. Okay. And that'll be between 1 and negative 1. All right, so this gives us a better idea. So one thing we can do is we know that constants go right through the inner product, or the dot product. In this case, I can rewrite this now as u comma v in our inner bracket, in our inner product notation. So, and this of course also is true here. It's u comma v in the inner product. It's true in either case. This is true for any inner product, not just the dot product. And what we'll do is we'll put u and divide it by that constant. So what we're saying here, of course, is the vector here, these two vectors are both length 1. They're unit length. And that's just stating that any vector, if you divide it by its own magnitude, will be a vector of unit length. And we're saying that then the inner product will always be bounded between 1 and -1. And so this gives us a nice notion of angle, right? Because we know that cosine of theta, it varies between 1 and -1. And in the middle point, so if theta is equal to pi over 2, i.e. 90 degrees, okay, we know that cosine of pi over 2 is equal to 0. And that's right in between -1 and 1. So we have a nice way of then expressing angle. So now, even for vectors in high dimensions, we have this notion of angle. We have a notion of angle, theta, all right? So we can actually equate the dot product with this cosine and say that, or the inner product, whatever the case may be, is equal to cosine theta. All right, and we can rewrite this a bit further and actually say that theta then is equal to the cosine inverse of u comma v over the magnitude product, the product of the two magnitudes. Okay. All right, so now we have a notion of angle even when we can't visualize our angles. All right, so for instance, let's do a quick example. Let's talk about those vectors again. v1, we'll go back to this simple example, which was 2, 1. No, I think I'm getting it wrong. Wasn't it 1, 2? Right? And v2 was equal to, oh, sorry, I'm using my old notation. Let's put round parentheses on this. This is now a vector, not an inner product, and that will be -2 comma 1. All right, so we want to take the dot product of these two, and of course we get 0. But let's try something different. Now let's try so of course the dot product of these two vectors is going to be 0, and that would imply then that theta is equal to pi over 2. So let's try another example. v1 is equal to 1, 1, and v2 is equal to 1, 0. Okay, all right. So I can draw a picture of what that looks like that. All right, we want to find the angle between them, and it should be pretty straightforward. So what is the dot product between these two? It's going to be, so v1 in this case, v2 is going to be equal to 1. And then the norm, of course, this is going to be square root of 2 times the square root of 1. So it's going to be square root of 2 on the bottom. And we can also write that as root 2 over 2. All right, and we know that cosine inverse of root 2 over 2 is going to be pi over 4. So that's the angle, pi over 4, or 45 degrees. All right, so that's nice. This might be review for a lot of people. But the idea is we can do this in any dimension. So now let's start with another example. of another vector, and we'll call it Vn, and it's going to be the vector. This is our little example in high dimensions of, and the vector is going to be 1, 1, 1, 1, 1, all the way to 1, and there's going to be, the vector will be, it's in Rn. And what we're going to do is make n bigger and bigger and bigger and see what happens to the angle. And then we're going to try another vector, un, and it's just going to be the vector 1, 0, 0, 0, dot, 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 all the way to 0. And it will also have n entries. It'll be in Rn as well. All right, so what's the dot product between these two? So we're going to set cosine theta is equal to un dot vn, and we're going to take the magnitude. It's going to be un product with the magnitude of vn. So un and vn, the dot product is pretty straightforward. It's going to be just 1 again, right? Because there's only one dimension where the two interact that have a non-zero, and those will multiply to get it just the 1. And likewise, un will be of length 1. But Vn, well, it's just, it's going to be the sum of 1 plus 1 plus 1. There's n of those. It'll be the square root of that, so there's n of those. So it's going to be square root of n, 1 over root n. Okay, so as n goes to infinity, as n gets bigger and bigger and bigger, we have a bigger and bigger vector. We have a higher and higher dimensional space. That's eventually going to go to 0. And that means then that it implies that theta n is approaching pi over 2. I.e., we're approaching orthogonality as these two vectors, even though they have one component where they are parallel. The rest of the one component that they share, the rest of the entries are mismatched, and so eventually we're approaching pi over 2 or orthogonality. So so these vectors, for any finite n, they're not orthogonal, but they're getting closer and closer to orthogonal. So now let's try another example. I'm going to keep Vn the same. Sorry, I'm going to make un. I'm going to change un. Now I'm going to make it so that every other entry is 1. Okay, and so now I'll just take n, and it's going to be, we're going to step forward by 2 places. Okay, so just by 2 dimensions. So let's take the dot product there. So we see that, so as long as n is even, we can get a good result here that, that the dot product, so cosine theta, the dot product will be n over 2, right? Because they share half of their entries are 1s, and they share those, and so it'll be half of them that we can do that. And then down below, we have root n. And now what's this one going to be here? What's the norm of this? The norm of un is going to be, of course, root n over 2. So it'll be root n over 2. And that will, we can combine these things together. We have an n over 2, and a root n times a root n becomes an n over root 2. So the n's will cancel, and we'll get root 2 over 2. So that would imply then that theta, for every n that's even, is going to be pi over 4. So with these two vectors, the angle for any n value, for any n even value, it will always be at a 45-degree angle, if we can imagine that in high-dimensional space. So those are some nice examples of what's going on with this dot product, this generalization of an angle for things that are in high dimensions. Okay, so now we need to reframe the discussion and bring it back to something that's going to help us solve linear equations, linear PDEs. So recall vector spaces again. And let's say we have some set vi in our vector spaces. So I equals 1 to n. And the thing about vector spaces, they allow for this notion of linear combinations. So we can always create some vector out of sums of these vectors in this set. So I'll say C1 V1 plus C2 V2 plus C3 V3 dot 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 plus Cn Vn. All right. So this is really nice, and we know that if Vi, if that set is linearly independent, what it means is that we can't get rid of none of these vectors are redundant. If we want to look at the set of all vectors that we can produce through these linear combinations, just adding up different weighted amounts of these vectors, is that there are no redundant vectors. So you've explored this idea before in your previous differential equations course, and we'll trust that you've remembered that enough to follow along. All right, so now let's suppose that the set has a stronger condition that these VIs are mutually orthogonal. So we'll call it an orthogonal set of vectors. So that means that Vi, Vj, the inner product of any of those is always going to be 0 for I not equal to j. Okay? So if you take two different vectors, two distinct vectors from our set, and we inner product them, we find out each one is orthogonal. So this is a property of our set. We're going to assume now we can create orthogonal sets. So the next thing we want to do, so naturally this property, so we can always so this is a condition that's stronger than linear independence. It goes beyond just mere linear independence. Mutually orthogonal is a much stronger statement. If you have an orthogonal set, by definition it is linearly independent, plus has more properties even than that. So what we want to do then is if we're given, the goal then is to be able to represent a given vector W. Again, this is handed to us. We have a vector, it lives in some vector space, and we want to represent it as a linear combination of our vectors in our set. And the question is, how do we do that? So I want to set up this sum here. So the goal then, so how? Well, we have to find, so the goal is we must find the CIs. All right, we need to find those CIs. So how do we find them? Well, now we have a nice tool. We have orthogonality. Of our VIs, and we have an inner product. So we have this inner product, and we have our set is orthogonal. So how do we find it? So what we say is the CIs are unknown. They're unknown, but we need to find them. So we need to find a way to compute the CIs. Well, we do this by setting up W. W is given to us. And we say then that, and we can write this sum. I'm going to write it in a more compact form. It's just going to be the sum I equals 1 to n of CI VI. Okay. So now what I want to do then is I want to find C1. What I'm going to do is take the inner product of V1 with W. And that becomes, we're going to replace W with this full sum here. And what we're going to do then, but remember the inner product had that nice property that it passes right through sums. Again, that is a giant sum. So it can pass through that entire sum, so that the sum can go outside. And remember, it also, scalar multiplications pass right through as well. So CI does that. And then we're left with only V1, comma, VI. And now remember the orthogonality property right here. All of these are 0 except for one of them. That'll become C1, V1, comma, V1. That's the only one. That's the only inner product that's left that's non-zero. So remember that W is given to us, and we know what V1 is, so that means that C1 is going to be equal to the inner product V1 with W divided by the inner product of V1 with itself. I contend you can do this for all of them. CI, of course, is going to be the inner product of VI with W divided by the inner product of VI with itself. Sorry, I'm running out of room there. So now we have a nice sequential way of finding all of the CIs. And so what would we do beforehand? So I'm going to just rewrite this. So before, without orthogonality, if we didn't have orthogonality, we would have W, which I'm going to call this vector W1 all the way to Wn. And we had this V1 times C1 plus C2 times V2 all the way to Cn times Vn. And we can rewrite this as the matrix with columns like so, times the coefficients all the way to Cn. So this would be a giant linear system, and this would be a matrix A, and what we'd have to do is use row operations to solve for CIs. Okay, so that takes a lot of work. It could be a problem that we'd have to use on a computer, but because VIs are orthogonal, we don't need to actually use row operations or do any of that heavy lifting to find the CIs. All we have to do is iteratively compute the CIs by taking inner products. Like so. So that is a really nice property. that we're going to exploit a great deal in order to solve partial differential equations. So to finish this off, I'll give an example of a particular set. So we'll talk about the set V1, V2, and V3. And it's going to be, these are going to be vectors in R3. Okay, so V1 I'll set to be 1, 2, 1, and V2 will be 1, 0, negative 1, and V3 will be 1, negative 1, 1. And so note, I'll put an asterisk up there, that these are orthogonal. So if you dot product any of these any two pairs of these vectors, you're always going to get 0. Okay, so now what I want to do is I'm going to be given this vector w, which is going to be equal to, let's do, the vector will be equal to 0, 1, 4. Okay, and I want to represent this in terms of a linear combination of these three vectors: c1 v1 plus c2 v2 plus c3 v3. All right. So again, the goal is find ci, c1, c2, and c3. All right. So we're going to use our formula. C1 is going to be equal to the inner product. In this case, the inner product is a dot product, V1, all over V1 dotted with V1. Okay, so we can easily do this. The dot product of V1 with itself is going to be 6. And the dot product of W with V1 is also going to be 6. So 6 over 6 is 1. So that's the first answer. C2. Well, the dot product of W with V2 is going to be negative 4. And the dot product of V2 with itself is going to be 2, which leaves us with negative 2. And C3 is now going to be, we can write that down as the dot product of W with V3 over V3, dot product with itself. And that becomes minus 1 plus 4 all over 3, which is 3 over 3, which is 1 again. All right, so there's a way we do this. So why do we care so much about these linear combinations? And recall, so the question, what we're going to do next with this, and we'll do it in a different video, is so why is this so important? Is we know that partial differential equations, what we're going to do is we can represent them as we're really focused on linear partial differential equations. Linear PDEs have a property is that if u, I won't call it a vector, x, y, z, comma t, and v, x, y, z, comma t are solutions to a PDE that's linear, then it has to be that C1 u plus C2 v is also a solution. And we're going to use this property of orthogonality to be able to express things. So in another video, we'll go over the same concept now, but u and v will be functions. So our vector space will no longer be R3 or Rn, it'll be function space. But we'll do that another time. So thank you very much.